Last time we already looked at integrals of the form some power of sine times some power of cosine dx, and we saw how to solve this such integrals completely. Namely, for instance, if n is odd, then what we do is we take out one sign and we write the rest. So if the power is odd, we can take out one sign, then the power will be even, and we can replace the rest by the formula sine square of x plus cosine square of x is equal to 1 in terms of cosine, and then we substitute u is equal to cosine of x. If m is odd, we do the same just for this part here, and if both n and m are even, then we can use the half-angle formulas in order to reduce the power of n and the power of m both by n half, and then we go on using the methods either looking again. You have three cases, so if you reduce here n by n half and m by m half, then again the three cases might be, okay, n half is odd, or m half is odd, or both are even, and in all three cases we know how to handle the integral. Now, so this is for such a class of integral. Another class of integral which can be handled quite similarly is the integral. So we have a tangent to the nx times secant to the mx. So this is another class of integral which can be handled similarly, because we know that okay, the derivative of the tangent is the secant square. Okay, we know that the derivative of the secant is secant times tangent, and we know that secant and tangent are related by 1 plus the tangent square of x is equal to the secant square of x. Okay, so using those three relations here, we can handle this class of integrals quite similar to this class of integrals. Namely, if we have, for instance, if you are in this case here, so if m is even, then you can take out a secant square of x, and you can rewrite the rest in terms of tangent. So if m is even, so assume that m is equal to 2k. So the given integral is tangent to the nx, and then the secant to the 2k x dx. Now, what we do, and assume also that k is larger or equal than 1. So in this case, we take out the secant square of x, and then we have here a tangent to the nx, and here we reduce the power by 2. So we have here minus 2. So we have here a secant of x square to the k minus 1 dx. Now we use this formula here in order to rewrite the remaining parts in terms of tangents. So we have the integral secant square of x, and we have here a function which is just in terms of tangent. Okay, and in particular, if we substitute now u is equal to tangent of x, which means that du is equal to the secant square of x dx, then this integral becomes very easy. Just the integral u to the n 1 plus u squared to the k minus 1 du. And this we can solve because it's a polynomial. Okay, so this is the first case. N is even, and the power is larger or equal than 1. M is even, not n is even. So this is the first case. The second case is, so here we use essentially this here, that the derivative of the tangent is equal to the secant square. Similarly, you can use this relation here. So here you have to take out, you have to separate secant of x times the tangent of x. So what you need is that both are there, okay? So n and m have to be both larger or equal than 1. And then you are going to rewrite what you have in tangent in terms of secant. But in order to use this formula, what you need is that the remaining part is, that what remains here is even. So what you need is n is odd. So n is odd, m larger or equal than 1. Then you can do similarly just by taking out this part here. And then, again, rewriting the rest in terms of secant and doing the substitution, and you will end up with a polynomial. Okay, so this is here the first case. Now the second case. So the second case is n is odd. So assume n is equal to 2l plus 1, and m is larger or equal than 1. So this is the second case, because in this case you have, okay, so we start with our integral. Now what we do is we take out a secant of x and a tangent of x. So the idea is here, because we know that the derivative of the secant is this here. And then we rewrite the rest. So here you have still a tangent to the square to the L, and you have a secant to the m minus 1x dx. Now, in order to rewrite this, you use this relation here. So you can replace this by secant square minus 1. So you have the integral secant of x, tangent of x, and here's secant square of x minus 1 to the L, secant to the m minus 1x dx. Okay, now everything, the remaining part is a polynomial in secant, and you do the substitution. U is equal to the secant of x, then du will be equal to the secant of x tangent of x dx. So everything becomes an integral over a polynomial is solvable. So we have, in two cases, we see it's very easy. Using those three relations, we have isolated two cases where it's very easy to compute this integral. Once more, namely, m is even, or n is odd, and m is larger or equal than 1, the case you see here. Of course, there are some cases which are overlapping. So in cases which are overlap, you can use both strategies. But still, a couple of cases are missing. And for all the remaining cases, you need something different. Okay? So it's not so clear. You do not have a general tool for the remaining cases. So in case, for instance, what are the remaining cases? For instance, integral we cannot handle by this approach here is, for instance, the integral over tangent to the cube of x. Okay, because if we have tangent to the cube of x, then of course we do not have the secant square to take out, and we do not have a secant times a tangent which we can take out. So in this case we have to rewrite the integral first, and then maybe can use something like this. So maybe let's discuss some of those cases which are not covered by those two cases. I'm not going to do examples for those two cases because it's trivial. So essentially, for those two cases, what you need is either a secant square or a secant times a tangent. Okay, and you need some properties for the rest. So, for instance, even the integral tangent of x dx is not covered. But this integral we already computed previously, so this is the ln of the cosine of the secant of x plus 1 plus a constant. Now, another integral which is not covered by those cases which I just introduced is okay, how to integrate the secant. Okay, so it's not so complicated. Here, for all those cases which are not covered by those two situations, you need some ideas. Normally, what you're going to do is you use the formulas, the relations between trigonometric functions. So, for instance, in this case, easy idea is, okay, you multiply everything with secant of x plus tangent of x over secant of x plus tangent of x. Okay, so you need to have an idea. For instance, here the idea is doing this here. Now, why is this helpful? So let's rewrite this to secant of x plus tangent of x. And the numerator becomes secant square of x plus secant x tangent of x dx. And the reason why this works is because you observe that the derivative of this here is exactly this here. Because the derivative of the tangent is this one, the derivative of secant is this one. Okay, so we will do the substitution u is equal to secant of x plus tangent of x. Okay, because we have the derivative of this as a multiplicative factor, and everything will become the integral du over u, which is very simple, ln absolute value of u plus c. So this integral is ln absolute value of secant of x plus tangent of x plus a constant. Okay, so this just tells you, okay, that in this case, you need some tricks in order to handle the integral. Okay, so those are the two cases, tangent, the integral for the tangent, the integral for the secant. Now, in our textbook, you see also worked out now the integral secant to the cube and tangent to the cube. But okay, let's maybe. So in our textbook, you see this one. Okay, next. But maybe let's already look at this one, where n is larger or equal than 1. Let's check out what we can do for this integral. Now, the idea is, okay, so maybe let's take out, if this is large enough here, okay, because we have already handled the case n is equal to 1. So if this is large enough, we can take out the tangent square, and then we have a tangent to the n minus 2 x dx. Okay, now we can rewrite the tangent in terms of the secant. So we have the integral secant square of x minus 1 tangent to the n minus 2x dx. Okay, and now you see, you can write this as the difference of the secant square of x tangent to the n minus 2x dx minus, and then you have the integral tangent to the n minus 2x dx. We do not have to bother too much about this one, because we assumed we know this already, and we want to compute this one. Okay, so this will give us again a recursion formula how to compute all those integrals, starting from the integral where n is equal to 0 and n is equal to 1. Now, and this one is easy to compute, because this falls into the two cases we just discussed, because you see that the secant of x is here with even power. So you take out this and you substitute the tangent, because the derivative of the tangent is this here. So for this one, u is equal to tangent of x. So you have the integral u to the n minus 2 du minus, and then this integral here. As I said, we do not have to bother about this integral here. Now this is computable now, so this is u to the n minus 1 over n minus 1 minus the integral tangent to the n minus 2 x dx. And now we replace u again by tangent. So we have tangent of x to the n minus 1 x over n minus 1 minus the integral tangent to the n minus 2x dx. Okay, and this solves all those integrals. Okay, so we can compute all those integrals by using this recursion formula. We just reduce here the order and write this out. So we iterate it, and depending on whether n is even or odd, we will eventually end up here with either the integral dx, which is computable, or the integral tangent x dx, which we just saw how to compute it. Okay, So this is another case which is not, you see this is actually not covered by our two situations I have discussed before. But using this trick here, okay, we easily get one integral which is covered by the two cases. So this frequently you have to use something like this. So any questions to this? Now our textbook, if you look in our textbook, it computes also this integral here. Okay. But again, maybe as an exercise, which is not part of the exercises, you can think about how to find the recursion formula for this case, using the same idea as is used in the textbook in order to handle this case here. Okay. So actually, here, for this case, if n is even, okay, it's more easier, okay? Because if n is even, we can take out the secant square of x, and the rest will be, the power of the rest will be even. Okay, so n is even could be handled more easily, but n is odd is the real troublemaker. Okay, and for n is odd, for n is equal to 3, for n is equal to 1, we know already. You just saw how to compute the integral. For n is equal to 3, you see it, you can find it in our textbook, and you can generalize the method from our textbook to general n, and again find the recursion formula. If you look in our textbook at the last page, very last page, look at the last page. Okay, is it the last one? You see many integrals worked out. Not the last one, the page before the last one, and you see that this integral is there expressed as an integral of secant of n to the secant of n minus 2 of x, right? 77. You are invited to prove it. You see that at the end of our textbook, you find the tables for integration. Okay, of course for the in-class homework next week and so on, it's not enough if you just copy the solution from there. Okay, you have to tell me how to compute it. But the most easiest way to solve the examples, the homework examples, would just be to look at the table and just to write out the answer. Because most of the examples we will discuss are summarized at the end. And in fact, if you go to the library, you can find whole books dedicated to many integrals, okay, worked out. I mean, the result, not worked out. You see the result. And you see for such integrals, okay, very frequently we have recursion formulas. So you try to express it in terms of something you can compute plus or minus an integral over the same quantity but n reduced. Okay, and once you know this, you can recursively find secant of x to the n. So for instance, if n is equal to 5, you have to know already n is equal to 3 and n is equal to 1, and then you use like similar to in the flavor similar to induction to find this integral. Okay, but I'm not going into details because you see the method anyway in our textbook. Now, a class of functions which is pretty similar is the following one. So you replace secant by cosecant, and you replace tangent by cotangent. Okay, similarly, you use the same approach. We have considered, because you know that the derivative of the cotangent is minus the cosecant square. Okay, and also the derivative of the cosecant is something like cosecant times cotangent. I don't remember. But you use those two relations, and you have also a relation between those two, similar to secant and tangent. And you use those three relations, and you can essentially, if n is even, then you can take out a cosecant of x squared, and you will write the rest in terms of cotangent. And if m is odd, and n is larger or equal than 1, then you take out the cosecant of x, cotangent of x, and you rewrite the rest here in cotangent in terms of cosecant and do the substitution. Okay, so you have again those two cases. So this case, this is very similar to the previous situation. And using those classes of functions we have, or those tricks we have discussed so far, you can handle many other integrals which involve trigonometric functions. For instance, another one would be this one. Okay, so how to solve this? Now, the obvious trick to do this is you multiply numerator and denominator by cosine of x plus 1, because then you have here cosine square of x minus 1 dx. Okay, now you can rewrite this in terms of the sine, so you have the cosine of x plus 1, and here let's take out the minus. Okay, now you see that the first part of the integral, minus integral cosine of x over sine square of x dx. Okay, substitution, because you see that the derivative of sine is the cosine. Okay, so substitution here, and for the second part of the integral, minus the integral, and this here actually is the cosecant square of x dx. This falls into this category. Okay, but this is easy because this is just a cotangent. Okay, so here you use substitution. So for the first one, you use u is equal to sine of x. So du is equal to cosine of x dx. So you have here minus 1 over u square du. And here for this one, you have cotangent of x. Okay, and of course this is easy. So this is easy to solve here. So you have minus u to the minus 1 over minus 1 plus cotangent of x plus c, and then you plug this in again. Okay, so you see that also such integrals are manageable if you use some tricks. It's not very complicated. If you have a little bit of experience with this, then it's no problem. Essentially, all integrals, okay, where you have a rational function in terms of sine of x and cosine of x. You see a rational function, so you see some polynomial divided by another one, and both polynomials are in terms of sine of x and cosine of x. Okay, such functions can all be handled. Okay, we will later on look at the substitution which will handle all those cases. Okay, so any questions? But before we can do so, we have to discuss. This will not be done in the next section, but in the section after the next section, we have to discuss how to compute the integral of rational functions, and also this is completely manageable. Now, another class of integrals which can be completely solved are integrals like this one, sine nx cosine mx dx. Okay, the reason why such integrals are also can be completely managed is because you know there are again certain identities for trigonometric functions. So for instance, this one, you can write this as 1/2, and then you have sine a minus b x plus sine a plus bx. Right, sine, cosine. Okay. And you have similar relations for. You find them in our textbook. You have similar relations, as you know. If you do not have a sine and a cosine, but two sines and two cosines, you have similar relations. Now, you can use this in order to rewrite the integrand in this form, and this is more easy. So for this integral, what we get is 1/2, and then we have the integral. So we have here the sine of n minus m x plus the sine of n plus mx dx. Now, a sum is always easier than a product. So you have 1/2. And for this integral, you have minus. So you can do a substitution here. But what you get is minus cosine n minus m x over n minus m plus 1/2. Here you have also minus. And then you have cosine n minus m x over n minus m. Plus. So for instance, if you are interested in, if you have also boundary conditions, if you go from minus p to pi, then you have minus pi to pi, then you evaluate this at minus pi to pi. Okay. You will discover it's equal to 0. So don't solve it like this, because you see that this function here is an odd function. Okay, so the integral must be 0. Okay, so you do not have to solve first this one, and then write it like this, and then discover it's equal to 0. You can. This is immediately clear from this integral. Okay, so always check whether there is symmetry. Okay, like today in the in-class homework. But the symmetry sometimes is different. Today in the second example, the symmetry is around pi half, not pi, not around 0, because the integral was from 0 to pi. So you use symmetry around pi half. You can solve it. It's always worth it to check for symmetry. Okay, so these are certain classes of trigonometric integrals which we are able to handle. Now, the next thing which is discussed in our textbook, or the next topic which is discussed in our textbook, is so-called trigonometric substitution. So this is a method in order to handle a large class of integrals. So essentially what we want to handle is this one. Okay. We want to solve such integrals. Now, and a is larger than 0. Now also, so essentially what we want to handle are integrals which involve something like this here, because the method we are going to use will be applicable to a quite large class of functions, all functions which involve somehow this kind of term. Okay, maybe also something like x over this term and so on, x squared over this term and so on can be handled with the same method. But maybe let's first look at this one. Now, the idea is, if you have seen the idea, you know how to solve it. It's just for the, if you haven't seen it, then this is a good example for integral. Okay, because maybe you will discover, okay, a good trick is to use this here. Okay, so you introduce a new variable theta, like this here. It's kind of a little bit different to the substitution rule we have used before, because before, for the substitution rule, we have written the new variable, okay, in terms as a function of the other ones. Here we do it somehow the other way around. Okay, the new variable is implicitly. Okay, that's why the textbook calls this inverse substitution. Okay, it's kind of it's about the same, but it's reading the substitution rule from right to left, not from left to right. Okay, so it's slightly different. You have to assume that the function you use here, okay, because this is some function, and you have to use that the function g is can be inverted. This is has an inverse function. This is important. Now, the reason why this works here, okay. So actually, if you do such a substitution, you also have to say something about the range of theta. We choose here theta. We always choose theta unless we have here some boundaries. Then we have to think about, because then it might be different. But okay, so we use theta in this range here. Now, the reason why this works is because of the formulas for trigonometric functions. Namely, this here can be replaced by cosine square of theta. So you see, if you compute the square root, you will get, because a is larger than 0, a times absolute value of cosine of theta Now if theta is in this range, the cosine is positive, so we can drop the absolute value. So that's the first thing. And we have also to replace dx by d theta. Now this is equal to a cosine of theta d theta. Okay, so what we get is, for this integral, what's the integral? And this integral is not complicated because we know how to solve them completely. That's why I discussed first trigonometric integrals involving trigonometric functions. Because here now, for this one, half angle formula and so on, the usual trick. We'll do it. Okay, so this substitution here is called trigonometric substitution. Okay, the method is called the method of trigonometric substitution. And this method can be used to handle a large class of integrals. Now, maybe I should stress here, okay? If you have given this integral, don't do this, okay? Because if you have given this integral, what is the answer? Because it's a circle, you compute the area of a semicircle, the area with radius a. Okay, so if you have such an integral, okay, don't do this. Okay, it's a waste of time. Okay, interpret it as an area, and you can immediately compute it. So there is a difference between the computing the indefinite integral and the definite integral. Okay. The definite integral can be much more easier because you can interpret it as a part of a circle. Okay, even if the range is if the range of integration is not from minus a to a, it's different. Okay, you're still integrating over some part of the circle, and you can use the area interpretation to quickly come up with the value of the integral. You do not have to go through those messy details. Because I remember for the homework from, I think you had to handle in last week, okay, some student used this kind of heavy machinery already to solve a very easy integral, which you could interpret as an area and then immediately come up with the answer. Apart from this situation, a couple of other integrals can be situations can be handled similarly. Okay, so for instance, if you replace minus here by plus, then because we just saw that 1 plus the tangent square of x is the secant square of x. So in this case, you will substitute x is equal to a times the tangent of theta. Okay, and similarly, if you have this integral, okay, then you also use this formula here, but you substitute x is equal to a times the secant of theta. Okay. In this case, you could use another substitution. Who can tell me another substitution which also works? In this case, you can use another substitution as well, which works just like this substitution. Who has an idea? You need something like something minus 1. Okay, something square minus 1 is getting easy because if you have this here, the reason why we choose the substitution x is equal to a times the sine of theta is because 1 minus the sine square is easy, is kind of easy. It's the cosine square. Okay, that's why we use this substitution. So here you need something square minus 1 is getting easier. Which kind of functions do satisfy this relation? Who knows the answer? You choose the hyperbolic cosine, okay? Because the hyperbolic cosine square minus 1 is the hyperbolic sine square. So actually this works as well. In many cases, much more easier than using this one, unless you like secant and like handling more complicated expressions. Okay, so those are essentially the three cases. Okay, we are going to discuss. The really simplification of this substitution comes from the fact that if you use this one, okay, then actually this class and this class is pretty similar. Okay, it's just the difference that here you work with trigonometric functions, here you work with hyperbolic functions. Okay, but pretty similar. And you can also handle integrals which involve such terms, as I have already stressed. So if you have something like here, x squared times this one, you can try this substitution. Okay, and this, in most of the cases, you will be successful. So, and those are essentially the three cases which are covered, which are called trigonometric substitution. Now, maybe let's look at some examples to see how this works. So, for instance, if you have this integral 1 over x squared square root of 9 minus x squared dx, okay, so we see that we have here this kind of we see here this kind of square root, okay, and whenever we have an integrand where we see something like this here, okay, the method of trigonometric substitution might be successful. Of course, you could end up with something which is much more complicated than the original integral, okay, but if the rest is like a rational function, okay, it's very likely to work. Now, so in this case, we substitute x is equal to 3 times the sine of theta, where theta is between minus pi half and pi half. Okay, so we saw already that this here transforms this square root, minus x squared, into 3 times the cosine of theta. Also, we have the dx is equal to 3 times the cosine of theta d theta. Okay, so everything becomes the integral. So we have here, okay, let's write it up. 1 over 9 times sine square of theta. And then we have here 3 times cosine of theta, and we have here as 3 times cosine of theta d theta. Okay, now this here can be cancelled out. And the rest is easy to compute, because the rest is 1 over 9. And then this you can write as cosecant square of theta d theta. Okay, and this here is minus the cotangent. Now what remains is to rewrite this back in terms of x, okay? Because our original integral is in terms of x. Here the answer is in terms of theta. We do not have a definite integral. We have an indefinite integral. So we want to rewrite this back in terms of theta. So you have to handle the cotangent of the inverse sine of x to the x over 3. That's why in the first or second lecture, okay, I discussed how to simplify such formulas. Now. You certainly remember the way to simplify such formulas. So if you plug this in, you get this is minus 1 over 9. And then you have here a cotangent of, and then you have an inverse sine of x over cube plus c. Okay, but this can be simplified by looking at the right triangle. Okay, so you have here the right triangle. Okay, you have here theta. Now. We know that the sine of theta is x over 3. Okay, so this must be x here. This must be 3. Okay, and this means that this length is here 9 minus x squared. So the cotangent of theta is equal to square root of 9 minus x squared over x. Okay, so you can rewrite this as, so the solution becomes minus 1 over 9 square root of 9 minus x squared over x. Okay, that's why I discussed in the second lecture how to simplify such formulas. Okay, it was not just a some nice exercises. Okay, this is something we will need here in order to come up with the final expression. Okay, so any questions to this? You see, this machinery can be used in order to prove that the area of an ellipse, maybe you have learned in high school the area of an ellipse is a times b times pi. Okay, and this machinery can be used in order to prove this. So if you have an ellipse, the x squared over a squared plus y squared over b squared is equal to 1. Okay, then, so this is, you know from high school this kind of guy, and you want to compute the area. Okay, then for instance, we can reduce this problem to computing the area of this piece. So we have to compute the integral from 0 to a. And now we have to solve this for y. So maybe I should do this first. Okay, so y is equal to plus minus square root. And then you have b squared times 1 minus x squared over a squared. Okay, so you see that the integral we have to compute in order to find the area. So okay, we just compute this piece here, so we go from 0 to a, and we just have to take the plus. So we have b times okay, and in order to solve this, you can use you could either use the machinery, or even more easier is you substitute x is equal to a times u. Then this becomes here b times the integral u from 0 to 1, and then you have here the integral 1 minus u squared, and you have here an a du. Okay, so actually you do not need really the machinery, because here you see this is what you integrate here is just a circle. Okay, and for a circle we know that this one part of the circle, 1/4 of the circle, is pi over 4. So you have a times b times pi over 4. Okay, so for the area you get a times b times pi. Actually, not a very good example I just discovered, because here you do not have to use the trigonometric substitution. But this example is worked out in our textbook by using the method of trigonometric substitution. Okay, but not really necessary, because using this substitution, okay, transforms the ellipse into the circle. Okay, so this is something maybe you have heard this in high school. So you see that in case where a is equal to b, okay, it reduces to the circle, as it must be. Because then, if a is equal to b, you have here a squared times pi. Maybe let's look at some more examples. For instance, also such integrals can be easily handled. So you have x squared plus 1 to the 3/2. Okay, so here in this case you also have a square root of x squared plus 1, everything to the cube. And essentially, whenever you see something like this, you can try the method of trigonometric substitution. It might work. Okay, so in this case, I have already explained that we are going to substitute x to be equal to the tangent of theta, because then we know that the tangent square of theta plus 1 is the secant square of theta. Also, dx is equal to secant square of theta d theta. Okay, so you plug this in. So what do we get? So here we have secant to the cube of theta. And in the numerator, we have this here. So secant square of theta d theta. Now, this integral is very easy because this is just the cosine, okay, which is the sine of theta plus a constant. And again, if you want to because what you have is the sine of the inverse tangent of x plus theta. And this here again can be simplified in terms of x by looking at the right triangle. I'm not going to do this just to save time. But you see that also in this case, you can easily use this substitution. Now, maybe I should stress here that if the original function is this one, and here are x, okay, of course you can use this method. You can use this method in order to handle such an integral, okay, but don't do it because it's you have a much easier method here. You substitute. Okay, so always check first whether you can substitute, okay. If I try to push this through, also possible. It's not complicated, but indeed much more complicated than just using this trivial substitution here. So just when encountering such an example, okay, it pays off to think a little bit first. Now another example is this one. So if you have this one, okay, so sorry, not this one, this one. Okay, and a is larger than 0. So as I have explained, you can use here two substitutions, either secant or hyperbolic cosine. So let's maybe check the hyperbolic cosine of theta. Okay, so in this case, you see that the root, okay, becomes a times hyperbolic sine of theta, and dx is a times. So the derivative of hyperbolic cosine is not minus the hyperbolic sine; it's the hyperbolic sine, no minus. Okay, so if you plug this in, what you get is the integral. So you see the integral becomes very easy, d theta. Okay, so the answer is theta plus constant. So the answer is the inverse hyperbolic cosine x over a plus the constant. Okay, now if you do the same, okay. If you do the same by using this substitution, secant of x, maybe I should work this out just to see what is the difference. So in this case, this square root x square minus a square is equal to a times the tangent of theta. Also, dx is equal to a times the secant. This should be theta of theta tangent of theta d theta. So in this case, the integral, maybe I write it here. So in this case, the integral becomes the integral over, so we have here a times tangent of theta, and here we have a times the secant of theta tangent of theta d theta. Also not very complicated integral. So this is the integral cosine of theta d theta. Hey, no. This integral we computed today. Okay, so this integral is ln absolute value of the secant of theta plus tangent of theta plus a constant. Now this, but we have to rewrite things back. Okay, so this will get something like okay. I'm not going to do this. You can write this back and you can simplify this expression here. Okay. Now the resulting expression you get, or maybe let's do this. So this is the ln of secant of the inverse secant. So this is just x over a. Plus, and this here we have to simplify the tangent of x over a plus a constant. No, the tangent of this should be the inverse secant. Sorry, the inverse secant of x over a plus a constant. Okay, and now this here, okay, you can again simplify it. So you have here the theta. Now, so the secant of theta is x over a. So you have here, this is not x, this is x, this is a here. So this one will be x squared minus a squared. So the tangent of theta will be x squared minus a squared over a. And you plug this in here. Now, you see that this expression looks very different from this one. Okay, but essentially, of course, those two expressions are the same. It's not very surprising because the hyperbolic cosine is defined in terms of exponential functions. So the inverse hyperbolic cosine, okay, can be computed in terms of logarithmic functions. So it must have such an expression like this here. I think we previously in one of our homework examples, if I'm not mistaken, we have computed an expression for the inverse cosine. You can compare it with this expression and can check out whether it's the same or not. It should be the same, of course, except of a constant. Okay, so you can also compare those two methods. You see, this would be much more easier. Okay, but here you have to accept things like the inverse hyperbolic cosine. If you're not so familiar with such functions, okay, maybe you would prefer stick to this here. But this is more This is also more complicated. This is an easy example. If you have a more involved function, okay, the substitution using hyperbolic functions might turn out to be much more easier. So any questions to this? Now, using this method, the method of trigonometric substitutions, also, of course, integrals like this here can be handled. The integral 1 minus x squared dx. Also, such integrals can be handled. You just have to complete the square first. So this is a method you already are familiar with from high school. So you write this as minus, and then you have x minus 1/2 square. So you see you have here already x square minus x. So actually it's plus here. So what? But if you multiply this out, you have this here minus x square. You have minus x, and then you have minus 1/4. So what you have to add is plus 1 over 4. Okay, so this is minus x plus 1/2 square plus 5/4. Okay, and you first rewrite it like this. So you have the integral, and then you have 5/4 minus x plus 1/2 dx here square. And now you use the substitution x. You just substitute everything. Okay, x plus 1/2 will be the square root of 5/2 times the sine of theta. Okay, because if you do this, then the square root of 5/4 minus x plus 1/2 square. Okay, if you plug this in, then you see you can take out half. And the rest is just the cosine of theta. And from our substitution, you see that dx is equal to square root of 5/2 cosine of theta d theta. And now you plug everything in, so what you get is 5/4. And then you have the integral of, no square root, of course, cosine square theta d theta. And this here can be easily handled by half-angle formulas. So also, even so, if you do not have strictly the form like a square minus x square or a square plus x square or x square minus a square, but you have a square root of a quadratic polynomial, okay, you can use this method in order to solve the integral. Okay, so any questions to this? Now you see this is quite powerful, okay? So we can now handle quite a lot of classes of functions using this technique here. Now, another class of functions which can be completely handled are rational functions. This is the next class of function we are going to look at. So rational functions. Okay, so our basic task is we want to compute the integral of q of x dx. Or let's call this f of x. F of x dx, where f of x is a rational function, so it's a polynomial p of x over a polynomial q of x. Okay, so for instance, we want to compute, in our textbook you see the example, for instance, we want to compute this integral here. The integral x plus 5 over x squared plus x minus 2 dx, something like this here. Now, the idea behind computing such integrals is a classical one. Namely, the idea is to first look at the integrand and write it as something which is more manageable, more simple. Now, in this case, you can find this representation here. Okay, so you can write it. You can write the integrand here. You can first, if you first realize, you can write the integrand like this here. You see that once you know this here, computing the integral is getting much more easier, because the integral here you can the integral over this, then it becomes the integral over this minus the integral over this one, and those two here. This is the ln of absolute value of x plus 2, and this is 2 times ln of absolute value of x minus 1 plus a constant. So the basic idea behind handling rational functions is first write them like this here, okay? But this is still not very precise, okay? I still have to discuss, okay? What do I mean? In which, how are we able to look at this and then write it like a sum of such simple fractions? And these simple fractions are called partial fractions. So the method is called integration of rational functions by partial fractions, partial fraction expansion. This is called the partial fraction expansion of the rational function. Now, you see that maybe it's still possible to. You see that actually the first step in using the method, okay, is p of x and q of x both have a degree, okay. Now you see here the degree of this polynomial is 1. Here the degree of this polynomial is 2. Okay. Now we have normally we call a rational function where the degree of the numerator is smaller than the degree of the denominator proper, and if this is not the case, we call it improper. Now the first step is, but you can always transform. So if the degree here is larger or equal than this one, you can always rewrite here the rational function as some polynomial plus another rational function where the degree here is smaller than this one, okay, which is called proper. So you can always go from an improper rational function to proper rational function. Okay. Now this is normally done by division, long division. Okay. So if you have here something like, if you do not have here x but x to the cube, okay, then you first divide this polynomial by this polynomial with remainder, and rewrite this as some polynomial plus the remainder over this one. Now, so because of this step, we can always assume that the function we are going to treat is a proper rational function, okay? Because we always first can divide and take out the polynomial part. The polynomial part can be easily integrated. So that's the first step of the method. The second step is the method to factor. The second step of the method is to factorize the denominator. So the reason why I chose this these two partial fractions is very easy, is because I can write this here as, I can factorize the denominator like this here. And this gives me an idea, okay, which partial fractions to involve into the partial fraction expansion. Now, it can be proved, we are not going to prove this, that every polynomial, so every polynomial can be written as a product of linear factors. These are polynomials of the form ax plus b, and what we call irreducible quadratic factors. These are polynomials of the form ax squared plus bx plus c, but you cannot, the irreducible here means you cannot write it as a product of linear polynomials. And for this you have to assume that p squared minus 4ac larger than 0. Then you have two complex zeros of this polynomial, or you do not have any real zeros of this polynomial, and you cannot decompose this as a product of two linear polynomials. Okay, so it can be proved, maybe in high school you have heard it can be proved that every polynomial can be written as a product of linear factors if you work over the complex numbers. Okay, so if you are over the complex numbers, every polynomial can be written as a product of linear factors. But we are working over real numbers because our problem is real. Okay, so we do not want to go to the complex numbers. If you are working over the real numbers, okay, then it can be proved that it's possible to write every polynomial as a product of linear factors and irreducible quadratic factors. And of course, you can prove this once you know what will happen over the complex number field, over the complex numbers. Okay, so if you know that over complex numbers you can write a polynomial as a product of linear factors, you just collect the factors which correspond to conjugate roots and combine them to a quadratic polynomial, and you have to prove this. But this is not completely trivial to prove this. Okay, this is called the main theorem of algebra. Okay, in algebra this is proved. For instance, because my time is over, so in the second step, the first step once more is to go from an improper, in case the rational function is improper, we go on to a proper rational function. The second step would be to write the denominator as a product of linear factors and irreducible quadratic factors. And next time I will explain you, once you know this, once you have figured out how to set up the partial fraction expansion and then how to find those coefficients. You can maybe think, because of this here, it is possible, for instance, to write this also. You can compose this actually. So it's not that you cannot write this as a product of polynomials. Because of this here, you can write this as a product of two irreducible quadratic factors. Okay, you can figure out how to do it. It's not so complicated. But if you wanna compute this integral here, you have to do this first in the first step. You have to write this as a product of two irreducible quadratic polynomials. Okay, so but next time I will show you once more how to find those coefficients and how to set up the partial fraction expansion, and we will see that using this method we can handle all rational functions. Okay, so any questions? If not, then we will meet on Monday.